In this lesson, we'll calculate the moment of a force about an axis using the vector method. First, though, let's review the idea. To find the magnitude of the moment around an axis, we do it by expanding this determinant. In it, the first row is the unit vector that defines the direction of the axis. This unit vector can go this way, or you can flip it around and make it go the other way. It really doesn't matter. In the second row, we have to put the position vector components. The position vector goes from any point on the axis to any point on the line of action of the force, and so any one of these four vectors can be used. Finally, the components of the force vector. When you evaluate this determinant, you get a number, and that of course represents our magnitude. If that number is positive, it indicates that indeed the vector direction, the sense of direction, is in the same direction as the sense of the unit vector. If we get a negative value, it simply means that the vector m of a goes in the opposite direction. Once we have this magnitude, including the sign of it, we simply multiply it by our unit vector to represent our moment in Cartesian vector form. Now let's use these ideas and we'll solve some problems. We'll start with this one. Here we want to determine the moment of this force around the y-axis. To solve the problem, of course, we have to identify the three vectors we need. One of them, of course, is a unit vector that defines the axis. And another one is a position vector going from the axis to a point on the line of action of the force. Do you see any of these? There are really two choices. The simplest one, of course, would be this one. It has two components, minus 1i and plus 3k. But there's one other one we could consider. Do you see it? Well, we can go from the origin, can't we? After all, it's on the axis, and it goes from there up to here. It would be proper. And that vector, of course, would have three components, minus 1i plus 2j plus 3k. But we won't use it because this one is actually simpler. So let's write these out. For the unit vector for the axis, we simply have 1 times j. And for our position vector, as we've already said, that's minus 1i and plus 3k. We also have the force already specified, so let's put it in and evaluate the magnitude of the moment. What goes in the first row here? Well, there'd be 0, 1, and 0. Those are the components of our unit vector. The second row, we put minus 1, 0, and of course 3. And finally, the components of the force go in the third row, minus 5, 3, and of course 6. Now all we have to do is evaluate it. Taking this term first, of course that's 0. And actually that 0 is multiplied by its minor. I'd have 0 times 6 minus 3 times 3. But again, the multiplication gives us 0. Now let's consider this element. There we have minus. Don't forget add. And then we put this term, which is 1. And then we multiply that by the evaluation of its minor. Crossing this column in this row, we have minus 1 times 6, which gives us minus 6. And we subtract from that minus 3 times minus 5. That gives us plus 15, doesn't it? Now that's complete. And we have one more to go, and that would be this term. And that's 0, of course. So putting in the plus 0 just for completeness. But just to show you everything, we cross this column in this row, and we multiply this 0 times minus 1 times 3 minus 0 times minus 5. But again, we get 0. Anyway, working this out, we get our result, and that's minus 9 Newton meters. Understand, though, that the minus sign indicates that the moment actually of this force around this axis is not going to be directed in this direction. Rather, it will go the other way. So if I were to want to write the moment as a Cartesian vector, that moment, m sub a, is equal to its magnitude, which we've calculated to be minus 9 here. Actually, the magnitude is always a positive number. But I'll put in the minus sign, and I'll multiply it by our unit vector, which is simply j here. I'll close my brace like this, and then I'll report the units. And that's how you solve it. All right, now let's consider this one, where we want to find the moment of this force around the AA axis here. Well, to do it, we have to define our axis using a unit vector u sub a, and we need a position vector. There's really only one to choose, and that would be this one. Let's write these out. U of a can be determined. The magnitude of it is 1 unit. Along the x-axis, I'd have to write minus 3/5 I. So let me put it in. Minus 3/5 I, by the way, is minus 0.6. And then we have the j component, and that component must go this way in the positive j direction, and it would be plus 4/5 j. And of course, 4/5 is 0.8. There we go. R, of course, is easy to get. That's equal to 3 times k. We also know the force completely here, so now we can proceed to go ahead and find our moment. Putting in the values we have, of course, up here, minus 0.6. We have 0.8. And we have 0. Our R vector, of course, would be 0, 0, and 3. And finally, our force vector, minus 3, 2, and 4. Now all we have to do is evaluate. We have this term. That would be minus 0.6 and we multiply it by the expansion of its minor. If I cross this column and this row, I have 0 times 4, which of course is 0, minus 3 times 2. Result of all that gives us minus 6. Now we'll do the next one. We have minus, don't forget it. And now we write 0.8. And now the expansion of its minor. Across this column and this row, we have 0 times 4 minus 3 times minus 3. And that gives us 9. And one more to go. And I think you'll agree that would be equal to 0, won't it? Actually, it's 0 times the expansion of its minor. Crossing this column and this row, we have 0 times 2 minus 0 times minus 3. So indeed, it is 0. If you do the arithmetic here, you'll get your result, and it comes out to be minus 3.6 Newton meters. And so here again with the negative sign, it simply means that the moment of this force around this axis will be going opposite to u sub a. And we can express the moment as a vector, of course, by simply taking this number and multiplying it by the unit vector, the direction in which it acts, and we'll get our result. All right, here's our final problem. We want to find the moment of this force around the AA axis here. Well, to do it, of course, we need to define our axis with a unit vector, and we need a position vector we can choose going from the axis to the force. Do you see one of them? This will work, but there's another one, isn't there? This guy. So we can choose either one of these two, and we get the same result. And it really doesn't matter here which one we pick, because each one has really just two components. Let's work them all out and see what happens. So first, the unit vector. Well, you can see that a vector extending from here to here is going to be 5 meters long. And if I take that and divide into the components of the position vector, in other words, 3i and minus 4j, I get my unit vector, don't I? And that, of course, would be then 3/5 I, or 0.6i. And we'd have minus 4/5 j, or minus 0.8 j. Now our position vectors. Well, the one going here is defined by minus 3i, and of course, plus 2k. And now we have the other one. Can you tell me what that one would be? It'd be minus 4j and plus 2k. So let's put it in. And now we have the needed vectors for our expansion of the determinant. Our force obviously has been reported already for us, so we don't have to fool around trying to develop it. So first we'll choose, this is our position vector in setting up our moment. In the first row of the determinant goes 0.6, followed by minus 0.8, and of course 0. Now the components of our position vector, minus 3, 0, and 2. And finally our force, and that of course is 30, minus 20, and finally 50. There we are. But rather than using this position vector, we can also use this one. So let me set it up as well. 0.6 minus 0.8, and finally 0. And now we put down here 0, minus 4, and 2. And one more time, the force, 30, minus 20, and of course 50. Now you can expand either one of these two determinants, and when you do, you get the results here. I recommend that you stop the video and you do that. Prove to yourself that the expansion of this determinant will give us our result, and also expand this one, and magically you'll find out it'll turn out to be the same number. What's the negative sign mean? It means that the moment of this force around this axis doesn't go in this direction, rather it goes the other way. And again, if you want to represent the moment around the axis as a Cartesian vector, what do? You take this number, this minus 144, and you multiply it by the unit vector right here, and you get the answer, of course. And that's essentially how we do these problems. And so now we'll end our lesson.